Examples. Number 1, evaluate the following. Part A, the integral from negative infinity to 0 of e to the x dx. It can be represented by the graph as a graph of e to the x, and we find the area under the graph from negative infinity to 0. The lower limit is negative infinity, which is type 1. So we introduce the notation A and take the limit as A approaches negative infinity to find the value of this improper integral. Now we have the limit of the definite integral from point A to 0 as A approaches negative infinity. The integrand is e to the x with respect to x. Next, find the antiderivative of e to the x, which is e to the x. Lower limit A, upper limit 0. Substitute the upper limit 0 and the lower limit A. E to the power 0 is 1. So we have 1 minus e to the A. As A approaches negative infinity, e to the power A approaches 0. So the value of the limit is 1, which is the real number. So we say this limit does exist, and the improper integral converges. Example B. The integral from 1 to infinity of natural log x divided by x squared with respect to x, as we see the upper limit as infinity. From the figure, introduce the notation b and take the limit as b approaches positive infinity. So this integral becomes the limit of the definite integral from 1 to b as b approaches positive infinity. Evaluate the definite integral. As we have natural log x divided by x squared, we use by parts. The natural log x divided by x squared, or we can write it as natural log x multiplied by x to the negative second, which is the product of the two functions. Use it to identify the two types of the function to define the u and the dv. The natural log as the L, x to the negative second as the algebraic, or the A. So we let u be natural log x and x to the negative second as a dv. For the by-part technique, the integral of the u dv equals u times v minus integral v du. For u equals natural log x, du is 1 over x dx, and the dv as x to the negative second dx. V is the antiderivative of x to the negative second, which is negative x to the negative first, or negative 1 over x. Put in the by-parts formula, the u times v, which is natural log x multiplied by negative 1 over x minus the integral v, which is negative 1 over x multiplied by du, which is another 1 over x dx. Simplify to be negative natural log x divided by x plus the integral of x to the negative second with respect to x. And then the antiderivative of x to the negative second is negative 1 over x. Bring it back to the main part of the problem. The antiderivative that we just got is negative natural log x divided by x minus 1 over x. Lower limit 1, upper limit b. We see the negative sign as a common sign. Take the negative sign out of the limit just for our convenience. And then the inside of the parenthesis becomes natural log x over x plus 1 over x from 1 to b. Take the limit as b approaches infinity. For the upper limit, we have natural log of the b divided by b plus 1 over b subtracted by the quantity from substituting the lower limit, which is natural log 1 divided by 1 plus 1 over 1. Natural log 1 is 0. Now we are going to find the limit as b approaches infinity of natural log b divided by b plus 1 over b minus 1. For the second term, as b approaches infinity, 1 over b approaches 0. The first term, use L'Hopital. We have 1 over b for the numerator, the 1 for the denominator, or we are going to find the limit of 1 over b. Take the limit as b approaches infinity. This term approaches 0. Therefore, the limit value of this is negative sign of negative 1, which is positive 1, which is a real number. So the limit does exist. And we can say the improper integral converges. Part C, the integral from negative infinity to positive infinity of 1 over 1 plus x squared with respect to x. As you see the lower limit and upper limit in the infinity form, we're gonna use the point C, which is the real number on the real number line. Let's pick the point 0 as a C. And this improper integral can be rewritten as the sum of the two integrals, which is from negative infinity to 0 and from 0 to infinity of 1 over 1 plus x squared. And then the first one, introduce the notation a as a lower limit. So from a to 0, take the limit as a approaches negative infinity of 1 over 1 plus x squared with respect to x. For the second integral, introduce the notation b and take the limit as b approaches infinity and b as the upper limit. So integral from 0 to b approaches positive infinity of the function 1 plus x squared with respect to x. The antiderivative of 1 over 1 plus x squared is the inverse tangent of the x evaluate from a to 0 for the first integral. And similar for the second integral, we take the limit as b approaches infinity of the inverse tangent of the x evaluate from 0 to b. Substitute the value of the upper limit and lower limit of both of them. We get the inverse tangent at 0 minus the inverse tangent at a for the first group, and the limit as b approaches infinity of the inverse tangent of the b minus the inverse tangent of 0 for the second group. Inverse tangent at 0 is 0. So take the limit as a approaches negative infinity of negative inverse tangent of the a plus the limit b approaches infinity of negative or positive inverse tangent of the b. Recall the graph of the tangent. As x approaches negative pi over 2, the graph approaching negative infinity. The other side, as x approaches pi over 2 from the left, the graph approaching positive infinity. So for the first one, as the inverse tangent of the A approaches in negative infinity. Therefore, the first one approaching negative of negative pi over 2. The second one, the inverse tangent of the B, as B approaches infinity. So the value approaches pi over 2. The combination of these two becomes pi as a result.